Hello, grade nines. Today we're going to talk about relationships and data. Um, Yesterday we played around with relationships and looked at pieces of data and saw if there's any connections. Today we're going to go a little bit further. Um, we're interested in what the shape of the relationships is, or if there are different types of relationships, and how can you tell? So that's what we're going to look at today. We're going to do it by through an example here about a stone being dropped off the top of a tall building. So someone's at the top, they chuck it out there, and two sets of data were recorded. So the first table here, at every second, they're able to calculate the speed of that rock as it's dropping down. The other thing that they're able to calculate every second is the distance, how far it's gone from the top of the building. Okay, so this is two bits of information that we're interested in studying and seeing if there's any difference between the relationship between time and speed and a different relationship between time and distance, and compare them and see what we can tell. So one of the things you'll probably notice is the pattern that's going on here. So you see at 0 seconds, it's 0 speed. 1 second, it's 10 meters per second. 2 seconds, it's 20 meters per second. At 3, it's 30, and so forth. It's a very predictable pattern. Okay. What we're going to do is investigate the rate of change, how the speed changes every second. So you look at it, and going from 0 to 10, it's a change of 10. Going from 10 to 20, it's a change of 10. This is something called the first difference. The first difference is something we're going to calculate a lot today. And so it calculates the change going from here to here. So naturally, if we're going from 0 to 10, the way you can do that is subtract where you are minus where you were. So if I'm going 10 meters per second now, and I used to be going 0 meters per second, then that's 10 minus 0, and that's the change of 10. Similarly, if I'm now going 20 meters per second and I used to be going 10, I can subtract 20 minus 10, and I get that the change is 10. So that's why this is called first difference, because you're actually subtracting the one you're on minus the one before it. Now, I don't imagine we have to actually do this written part out every single time, because I think you can do it a little bit in your head. 30 minus 20 is 10. 40 minus 30 is 10. We don't actually have to write that down. And 50 minus 40 is 10. The other way you can imagine is the first difference also describes how much it's going up by. And you see it goes up by 10, up by 10, up by 10, up by 10, up by 10. So the first differences are all 10. Okay, so that's something called the first differences on this relationship. And there obviously is a connection between the speed and time, and it's described in a certain way. Let's look at this other relationship. There's a connection between the distance that it's fallen and the time. And let's try and calculate the first differences for this. So at 0 seconds, we're at 0 meters. And a second later, we're at 5 meters. So the difference there is we went up by 5. Again, we could do the subtraction, 5 minus 0, and get 5. So what's the jump from 5 to 20? Well, hopefully you'll see that it's actually 15. And that 15 is coming again from where you are now, which is 20 meters, minus where you were at the start, and it was 5. And so 20 minus 5 is 15. So the change from here to here is 15. Again, we don't have to necessarily write this out every time, but the jump from 20 to 45, I think you can see, is 25. The jump from 45 to 80 is 35. And then the jump from 80 to 125 is 45. And you get these first differences. And these obviously look a little bit different than this. So this relationship here is different than this relationship, even though there is a connection between the two. So this is calculating first differences. And at the end of this lesson, we're going to do a lot of calculating first differences. Next, I wonder what would happen if we graphed this. So I've got these two graphs, and you'll have to forgive me. It's not very accurate because I was doing this using my mouse. So just forgive me with the scales and things like that. But I'm pretty happy with how it turned out. But we're going to graph the first relationship here, which is the speed versus time, and the second relationship here. So if I go back to our data set and I take all these points, 0, 0, 1, 110, 220, and so forth, and graph it, we're going to get this. And if I go back and do the same thing for the distance one and plot all the points there, it ends up looking like this. So very different relationships. Now you remember yesterday you were asked to draw a line of best fit. Well, I think I'd be really confident in drawing a line of best fit for this data. It would go something like that, perfectly straight. But could you draw a line of best fit here? Well, sure you could, but it'd be very difficult to do, and it doesn't really represent this pattern. I think you can see that there is some sort of pattern going on here, but it's not a straight line. I think the pattern would, for this, might look something like that. Okay, like a curve instead of a straight line. So these two relationships end up being very different. This one, you can draw a line of best fit, and this one, you can draw a curve of best fit. So the line of best fit, if you can draw a line of best fit, we call these relationships linear. Linear being like a line. And if it's not a straight line, what we're going to call them right now is nonlinear, not a straight line. Okay? Now, you can see that this actually makes a nice curve, and there is a pattern in this data. But this pattern is a grade 10 pattern. Okay? It's actually called a quadratic. But we're not going to be studying these types of patterns this year. We're going to save that for grade 10. But what we have to be able to do is tell if the data and the relationship that we're studying, if it's a linear one or a nonlinear one. Because if it's a linear one, we can study it and do some more stuff with it in grade 9. But a nonlinear one, we can't be as confident about using that data. So, what are some of the advantages of linear relationships, which is this one, and nonlinear relationships? Well, the first thing you can see, there's a big difference here about the first differences. You see in this case, the linear one goes up by tens. Because if we look back at our graph, this graph is going to go up by 10, up by 10, up by 10, and it's going to follow that straight pattern, up by 10, up by 10, up by 10. Imagine steps in your house. If you go over 1, you go up 10. Over 1, up 10. Over 1, up 10. It creates this very straight line. The same's not true for this. If you go over 1, you go up a little bit. The next time you go over up, you go up a little bit more. The next time you go over, you go up a little bit more. The next time you go up, you go up a little bit more. The next step you go up a little more and more and more. This is a very different set of stairs. This is a straight set of stairs. These would be like small steps, and the steps getting bigger and bigger and bigger and bigger. This is a difficult pattern to really predict. And if you look at the graph, or sorry, at the tables, we could see those differences by just looking at the first differences. 10, 10, 10, 10, whereas these jumps are 5, 15, 20, 35, 45. I know there's a pattern here, and that's a grade 10 pattern. But this one is our grade 9 linear pattern. And we can have confidence in this. To the point that I can actually make predictions on this one with a lot more confidence than I can in this one. So for example, if I wanted to predict what the speed of this stone would be at 6 seconds, I think you all would agree, and with confidence, that the speed would be 60. But would you have the same confidence about what the distance is after 6 seconds? Well, we might be able to follow a pattern and make a prediction, but it's not quite as easy as this grade 9 pattern. Okay? And it's difficult to tell what 6 seconds would be. I think it would be, 180 maybe, but I have less confidence in this than I do in that. So for linear relationships, you can actually make equations to model this. So go back to this. What do I do to 3 to get 30? And what do I do to 4 to get 40? And 5 to get 50? Well, it's pretty easy. I multiply by 10. So I can make a little equation for this, saying that the speed is 10 times the time. Can you make a similar easy step? Well, what do I do to get 2 to get 20? Well, that's times 10. But does that pattern work for here, 3 times 10? No. So what do I do to 3 to get 45? I don't know. What do I do to 4 to get 80? I don't know. What do I do to 1 to get 5? Well, here I have times 5, but that pattern doesn't hold true here. Here it's times 10. Do I do times 20? Nope, that doesn't work. It's very difficult to come up with an equation for this nonlinear situation. It's much easier to come up with equations for linear relationships. So this one, you could say something like this, you know, S equals 10t, where speed is S is the speed and t is the time. Because it's a linear relationship, we can do things like this. We can even describe it in words. The speed is 10 times the time. But we can't do that with that nonlinear relationship. And in linear relationships, you can make predictions really confidently. So like 4.5 seconds. Well, I think if we look here, I could say confidently what 4.5 seconds is. It goes up by tens. So if I go from 4 to 5, that's only halfway is 4.5. So halfway between 40 and 50 is 45. With confidence, I can say that the speed is going to be 45. Could you do that with distance? Definitely not. It's not halfway in between 80 and 125, the distance, because the pattern isn't a straight line. It'd be really hard to guess what that number is. I don't know, is it 100? Perhaps, but I can't say confidently. You can really visualize this on the graph. At 4.5 seconds, I can confidently go over and say it's 45. But here at 4.5 seconds, I don't know what that number is. I mean, I can look at the graph and I can make a guess, 90 maybe, but it's not definitely not halfway between the 80 and the 120 or the 125. It's definitely not halfway in between there. I was guessing something like halfway in between being 100. Well, it's actually less than that. I don't have that confidence in this nonlinear one. Okay? But if it's linear, you can do stuff like this. You can use our equations, our algebra. At 4.5 seconds, t is 4.5. You plug that in, you get 45 seconds, just like we predicted. Or you could put in your 75 for s, divide both sides by 10, and get that it's 7.5 seconds. All of these can be done confidently with linear relationships, but not so much in nonlinear. So, in general, what we're discovering here is if you notice that the first differences are the same, that means the relationship is going up by the same amount and the jumps are all the same, that the relationship is linear. But if the first differences are different, then the relationship is nonlinear. They don't jump up by the same amount, so it won't result in a straight line. Okay, that's part 1 of our video. You can save for a second and we'll be watching part 2 in a second.